Hello everyone, I am Dr. Purnima Tiwari, Assistant Professor of Mathematics, Department of Science, the Bhopal School of Social Sciences. In previous video for this topic, Fundamentals of Graph Theory, we discussed several properties and types of graph. In today's video, we will continue with the same topic, and here we'll discuss about complete graphs, regular graphs, directed graph, and handshaking lemma. Let us start with the definition of complete graph. A simple graph G in which there exists an edge between every pair of vertices is called a complete graph. Here you must note down that this concept is defined only for a simple graph. And if we have a complete graph of n vertices, we denote it by Kn. Let us draw some complete graph. If we have to draw complete graph of 3 vertices, that is K3. So first we'll draw 3 vertex and we may label them as V1, V2, V3. Now you can see that there are 3 pair of vertices. One is V1, V2, second one is V1, V3, and the third one is V2, V3. So we have to draw edge between each pair of vertices. Suppose we draw E1 between V1, V2, edge E2 between the vertices V1, V3, and edge E3 between the vertices V2, V3. You can see there is an edge between every pair of vertices. So this is complete graph of 3 vertices. Now if we have to draw K4, that is complete graph of 4 vertices. So first we'll draw 4 vertex. Then we can draw either a rectangle or a square joining these 4 vertices. Now you can see that there is 2 pairs V1, V3 and V2, V4 which are not joined by an edge. So for the complete graph we have to join these 2 pairs. We may label the edges E1, E2, E3, E4, E5 and E6. So this is complete graph of 4 vertices. If we have to draw complete graph of 5 vertices, first we need to draw a pentagon. We may label vertices V1, V2, V3, V4, V5. Now we have to draw an edge between every pair of vertices. So we have to connect V1 and V3, V1 and V4, V2 and V5, V2 and V4, or V5 and V3. So this graph is a complete graph of 5 vertices. We denote it by K5. Now we have 2 important observations regarding complete graph. First, that the complete graph of n vertices has n minus 1 by 2 edges. That is Kn has n minus 1 by 2 edges. We may verify with the example. Here you can see for the K3 number of vertices are 3. If we calculate this term, n minus 1 by 2, will get 3 into 2 by 2, so we'll get 3. And we can verify there are 3 edges in K3. Likewise, we can verify for K4. If we apply this rule for K4, we'll get 4 into 3 by 2, that is 6 edges. So K4 must have 6 edges as per this rule. And we can see there are 6 edges E1, E2, E3, E4, E5, E6. Likewise, we can verify this result for K5. For better understanding, you may draw K6 and may verify this result. Second observation is that degree of every vertex in a complete graph of n vertices is n minus 1. That is, if we have this Kn, then the degree of every vertex will be n minus 1. We can verify. See, this in this graph we have K3, and if we calculate degree of V1, it is 2. Likewise, degree of V2 is 2 and degree of V3 is 2. So, in K3, degree of every vertex is 2. If we see this example K4, we can see degree of every vertex is 3. V1, V2, V3, V4. All the vertices are of degree 3. Similarly, if we talk about this K5, you can see degree of every vertex is 4. So, these are two important observations, that Kn has n minus 1 by 2 edges, and the second thing, degree of every vertex in Kn is n minus 1. Next definition is for regular graph. A graph in which all vertices are of equal degree is called a regular graph. And if degree of each vertex is r, then the graph is called r regular graph. Now, in the examples of regular graph, we can see that the previous graph that we draw for complete graph are also regular graph. So, if we talk about this K3, complete graph of 3 vertices, you may notice that the degree of each vertex is 2. Degree of V1 is 2, likewise degree of V2 is 2 and degree of V3 is 2. It means in K3 every vertex is of degree 2. That's why this K3 is 2 regular graph. And if we talk about K4, we may notice that degree of each vertex V1, V2, V3, V4 is 3. So, this K4 is 3 regular graph. Likewise, if we talk about K5, it is 4 regular graph. So, we can say that every complete graph of n vertices is n minus 1 regular graph. It means every complete graph is a regular graph. But converse of this statement is not true. We can always draw a graph which is regular but not complete. Its example is one of the famous graph known as Kuratowski's 2 graph. Now, to draw this Kuratowski's graph, it's a graph with 6 vertices and 9 edges. So, we may label those vertices as V1, V2, V3, V4, V5, V6. So, this is Kuratowski's second graph. It is called as K33. You can notice that degree of each vertex is 3 here. If we talk about degree of Vi, then it is 3 for I varies from 1, 2 up to 6. So, this graph is a 3 regular graph. But we can see there is no edge joining the vertex V1 and V2. There is no edge joining the vertices V2 or V3. Likewise, no edge in between the vertices V4 and V5 or V5 and V6. It means there does not exist an edge between every pair of vertices. So, this graph is not a complete graph. So, if we talk about this graph K33, it's a 3 regular graph, but it's not a complete graph. Next definition is for directed graph, which is also known as digraph. A graph G is equal to VE is called a directed graph or digraph if this V is same as in the case of undirected graph, it is set of vertices, but this set E is the set of directed edges, or we can say that this set E is the set of ordered pair of vertices. It simply means that if in the undirected graph we assign a direction to each edge, then the graph becomes directed graph or digraph. For the example of directed graph, first we can draw an undirected graph as this graph. This is the graph G is equal to VE with 5 vertices and 7 edges. Now, if we assign a direction to each of its edge, like this direction to edge E1, that is this edge E1 started with the vertex V1 and terminated at the vertex V2. We can assign any direction either in clockwise or in anti-clockwise to each edge. So, I assign a direction to each edge. So, now this graph is a directed graph. Next concept is handshaking lemma. It is stated as the sum of degree of all the vertices in a graph is twice of number of edges. So, suppose if we have this graph G is equal to VE and this graph has n vertices V1, V2, V3 up to Vn. These are n vertices and E edges. So, we consider a graph with n number of vertices and E edges. Then this lemma said summation I varies from 1 to n, d of Vi is equal to twice. We can prove this lemma by simple using one argument that each edge incident on exactly 2 vertices. That is, each edge contributes 2 to the sum of degree of vertices. So, whenever we get sum of degree of vertices, it will be twice of number of edges. We may verify handshaking lemma for any graph. Suppose I consider this graph G is equal to VE, where it has 5 vertices as V1, V2, V3, V4, V5, that is n is equal to 5. And the set of edges has elements E1, E2, E3, E4, E5, E6 and E7. That is, number of edges are 7. Now, first we have to calculate degree of each vertex, and we find that degree of V1 is 3, V2 is 4, V3 is 3, likewise V4 is 3 and V5 is 1. And if we sum up, that is, if we calculate this quantity degree of V1 plus V2 plus V3 plus degree of V4 plus degree of V5, will get 3 plus 4 plus 3 plus 3 plus 1. And this quantity is 14. That is, summation I varies from 1 to 5 degree of Vi, because here we have only 5 vertices, is 14, and to this 14 we can write 2 into 7 and value of E is 7. So, we can write it as 2E, which verify handshaking lemma for this graph. For better understanding of this topic, you may draw some complete graph, regular graph, and may verify handshaking lemma for some more graph. Thank you so much.